them would they prefer knife skills to still be integrated into our design, and they said that their topmost priority is just having the students cut no matter what, not necessarily teaching them life skills. Also, the teachers identified that the safety of students, the stability of the vegetables and hands, and the number and uniformity of the cuts made using the design were the major objectives that they had, and so these are the major objectives we translated into the UniSlice. It's designed with these objectives in mind so that it can be used by students as a tool to truly succeed within the kitchen.
To accomplish this goal, we created a solution that creates an assistant uniform slices. I'll provide a brief demonstration. We already have an apple set up for you. So what you do is you set it up to create a slice, rotate the thing down, and you begin to slice. To create a julienne, you set these blades up, right? And then you do the exact same action. As you can see, uniform slices. We'll now describe the iterative process that led to this design. So first of all, we bought a rough mandolin for the purposes of further understanding our reference design and to be able to have a higher fidelity prototype with which we experimented. Next, we researched further and created this handle as an addition based on our research. However, when we visited the Kohai Education Centre in order to validate our design, we found that it was simply impractical. And so using both the positive and negative feedback we gained from that experience, we developed this final prototype, which simply goes over here. And this prototype was created for the purposes of not only verifying the information we gained at the Kohai Educational Centre, but also to verify other aspects of the design. I will now briefly outline the important components of our prototype. First of all, we have the knobs, and then leg grips, next the adjustable blades, and finally the container, which Jake will now expand on.
So, one of the most significant things that we changed about the initial mandolin design is the overall container and holder. So this is the design that we came up with. This is the final design we're pushing forward. And we had two goals with this design: to stabilize the hand of the person using it, and to stabilize the vegetable inside the holder. So I'm going to start by talking about how the vegetable is stabilized within the holder. So the way we designed this is so that it's large enough to fit entire vegetables inside. As you can see, if I were to take an entire apple, put it in here, and put our lid on, the entire vegetable is encased inside. The only real limitation of this is when you get a long vegetable, like a cucumber or a carrot. There is some preparation needed in that case, where you need to either cut the vegetable in half or in thirds, whatever size fits inside the holder. The holder also has a spring-loaded bar on the inside, such that when you put a vegetable inside, the bar is pushed up, and the spring then pushes down on the vegetable. This is intended to keep the vegetable or fruit, such as the apple, against the surface of the mandolin at all times, so that you don't have to be pushing down with it with your hand. Now I'm going to talk about the stabilization of the hand. So both the students at Kohai, the teachers at Kohai, and additional research showed that large grips were more stable and easier to hold for people with disabilities. And so that's what we designed with. The intention of this handle is so that your hand is put on the entire lid, meaning there's a large gripping surface area. Also, we designed the holder to have a horizontal power grip, and a power grip is basically when you use all four of your fingers as well as your thumb in the pushing process. And this is used to maximize force. The design is also symmetrical, such that when we later integrate a dicing operation into our mandolin, the way this happens is you spin the lid 90 degrees and then you go through another motion in order to cut at a different plane, and so that's why it's symmetrical, so it's easy to rotate. This is our initial handle design. This is the one that we built off of our theoretical research and the one we intended to take to Kohai to validate. And so if you see this video over here, this is the students at Kohai trying to use the handle we designed. As you can see, a lot of the students are having trouble figuring out how to actually hold it, and then once they aren't able to apply enough force down the mandolin to actually cut the vegetable. And also, as you can see, there's a large torque on the top, so it's a lot of rotation. And as James presenting to you now, we did a bit of a FBD analysis of it. We found that the design of this was simply too tall to have the students do it stably. So that's something we tried to fix with our new design here. So we made two major changes from the one that we took to Kohai. We made it so that the place where you're applying force is constant height, no matter what amount of vegetables at the same time. So no matter if you have a full vegetable in there or you're on the last slice, the pushing is always going to be at the same level. Also, move forward, the application, the place you're going to be applying this force, such that it's closer to surface of the mandolin, and you'll be able to apply less torque to it.
So I'm going to talk about the general ergonomic and usability features included in this design. First, look to the recommended posture of the students. So the students are standing when using our prototype, and that's based on the observations we had at Kohai. So if you look at the video, Jack initially struggles to step the potato. He makes small headway, and then misses back. When he stands up, it's much easier for him to make cuts, as you see in a moment. And although I need to brace the man, or the teacher's bracing it, all the voice application is coming from Jack, and he's able to cut through the entire potato. The next student in this video is Emily. She initially struggled to cut all the way through a potato with a knife. She can now cut through the entire potato using the mandolin quite effectively. This is Emily cutting through the potato. So, based on additional research done on counter heights, we recommend that potential users who are unable to stand use the device at waist height. This is confirmed by our qualitative observations at Kohai. It must be noted the improvements we saw when letting students stand up was not just noted in Emily and Jack, two students in the video, nor noted for everyone who testing was conducted. That was across the board. The second design element I'd like to draw your attention to are the adjustability of legs. So in our design, there'll be a ratchet system that allows you to choose the angle that's best suited for the course application for you. And last, we have silicone grips attached to the base that stabilize the mandolin. That's the role that my hand does in the video. And this is to stop it from moving around. Silicone was chosen because its high coefficient of static friction suggests that it's better suited for this application. Now, Yanshin is going to talk about blades.
So another one of the main design modifications that we had to make over our reference design was we wished to design a mandolin that was capable of performing all three of the most common types of cuts present in the kitchen, which are slicing, julienne, and dicing, which as you saw by the demo earlier, only the first two of which can be accomplished by the reference design. So to accomplish this, we had to make modifications to two different sets of blades, the main mandolin blade as well as the julienne blade. So for the main blade, we realized that there were three real knife profiles to choose from, and we ended up settling with retaining the wedge profile that was already in the blade. Now, versus the chisel blade, it's less stable, but it also requires much less force to operate. And versus the concrete blade, it's less sharp, but it's also much more durable. So we found that this was a good compromise for us. Now, for the julienne blade, we made larger changes. Firstly, we increased the size of the holes where the blades pop out of the platform. This allows for easier cleaning, both by the dishwasher and by hand. Secondly, we replaced the plastic internal components, which we found to be weak and difficult to use, with metal ones that increase the durability as well as the usability. We also made all of the blades double-edged to allow for the cross-hatching that's required for dicing. And finally, we replaced the current set of one julienne blade with 2 rows of adjustable blades, each with 4 settings, which are adjusted using the knobs on the side.
So I'm going to talk about knob design. So we set out to make the knobs attached to the side of the mandolin as accessible as possible. So we made the following changes. We added grooves to make them easier to grip, we enlarged them to make them easier to grasp, and we moved them away from the side of the mandolin. All of the modifications were made on the basis of recommendations from stakeholders, external research on grips for people with tremors, and US Army anthropometrics. We talked to a subject matter expert, Vicky Commissar, about the design choices, and her reviews about the knobs as the knobs were generally favorable. She recommended that we color code the knobs to add some sort of logo to suggest their function. And this is an improvement we'll definitely incorporate into our future prototypes. It's actually included on the scoreboard vehicle, but does not exist on the cab models. Her biggest recommendation, however, was that we use levers instead of knobs because those are better suited for people who have difficulty with grip. So a good analogy are these 2 door handle designs, and the lever-shaped handle is better suited for those with difficulties gripping versus the curved knob. This recommendation is made last moment, and so it's not been incorporated into any of the designs or models you see in front of you, but it's definitely an avenue of improvement that we're looking into. There are, however, so many other great aspects of the design that we need to talk about, and now Jay is going to do that.
The first of these aspects is that the mandolin is dishwasher safe. This is necessary as it enables the user to wash the prototype without putting their hands at risk of being cut by the blades. Next, we added stoppers to the rims to prevent the container from sliding out. As we were testing the initial design, we found that the container actually slid out quite often, which I will demonstrate to you now. It's quite simple to do so. The stopper circumvents this problem altogether. Finally, we also implemented notches to the top of our design, which indicate which angles to rotate for dicing. It also adds as a bit of an impressive cue to help with the intuitiveness of the design. Now I'll pass it on to Jake to discuss the process.
So you may be asking yourselves, how did we get to where we are today? Over the entire semester, we've been using different design tools and engineering tools in order to learn about what we wanted to include in a final design at every stage of our design process. So, starting with our initial divergence, such as brainstorming, Yanchen, can you go one slide forward? And another method we use called forced connections. We started realizing that there were certain ideas we wanted to include in a final design no matter what. These two features were restricting the axes in which the hand and vegetable can move in order to increase stability of both the hand and the vegetable, and to reduce the amount of student involvement with the thickness of slices. So we realized that having the students manually figure out how thick a slice should be was difficult, so we wanted to come up with a more automatic way of determining slice thickness, such as you can see in our final design. Moving on to our convergence, at every stage of our convergence, we found that combining different aspects of different designs into one design was really useful for us. So, as you can see from our Q chart analysis, this is a Q chart we ran at an early stage of convergence. And one thing that we got from this is that a lot of our designs had similar features. So the Mandoline and this this modified pizza cutter idea we had, both had restricted vegetable motion. But one thing we also got from this is that adjustable blades from the Mandoline could be similar to ones from food processors. So food processors have many different attachments that change the types of slices you get from a food processor. And that's kind of how we came up with the idea in order to apply that to the Mandoline. We also learned through representation. So by building our prototypes, we actually verified that some of them were simply unusable. So what you can see back here is an initial prototype for the pizza cutter design. Essentially, we couldn't find our pizza cutter, but I'll model with scissors. So essentially, a pizza cutter would be here, which would go back and forth, and then this was a conveyor belt that automatically moved the vegetable forward. And from this, we realized that having to both move the pizza cutter and move the conveyor belt with a button would be a very difficult process and very confusing for some students. And so that is essentially how we realized this design was unviable. Another example of this is our handle design. We took this to validate, and by trying to validate it, we simply realized this prototype wouldn't work. So we learned from our representation. We also learned from our verification and validation processes, which Yanchen will now talk about.
Now, using all of this groundwork that we've done in design and research, we took the Mandoline design that we had settled on, we purchased the Mandoline that you see here on Amazon, and we set about designing a new handle based on the ergonomic research that we had, stating that a thick vertical grip would be the easiest and most comfortable grip, as well as reducing strain on the hands and the wrist. So we took this design to Kohai with the objective of showing that this was the ideal design. We had each of 6 students cut different vegetables using this design, and while we didn't have as much time as we would have liked, we learned a lot from this process. We realized that the original design, while looking great on paper, led to lots of instability and was difficult and unintuitive for the students to use. We also realized the importance of posture in our design, which wasn't something we had really considered before. As we saw in the earlier video, many students struggled to cut while sitting down, but it became very easy while standing up. So we came back from this process, we boiled down everything that we had learned, and we put together this list here of current design elements, assertions, and observations related to the prototype, our testing, and our steps going forward. And we submitted this to be verified by the Kohai administration and staff, which it was. So now we were satisfied that we've had a design that was likely to be accepted by the community. We set about discussing the verification of key metrics. So we'll start with safety. Through our discussions with the Kohai staff, it came out that safety was the #1 driving metric for this entire design process. Now, due to our fully enclosed design of the vegetable holder and handle, we completely isolate the hands from the cutting surfaces. This, plus the safety box on the blades, as well as the machine washability of the entire unit, fulfills the metric of reducing potential contact between the hand and the blades. Now, we need to understand that while this design reduces the chance of injury, it also cannot completely eliminate this risk, as the blades are still sharp and present due to the need for effective cutting. It simply means that under normal operating circumstances, injuries are much less likely compared to knives. Secondly, stability was also one of the main issues we addressed. Stability is one of the main reasons we chose the Mandoline over other similar designs, simply by the nature of its design with a fixed cutting platform, as well as a fixed handle on rails, and a fixed vegetable using a spiked holder, it means inherently increased stability over other such designs. Through the use of the bounding box test dictated by the metric and our own qualitative observations during testing, we realized that the Mandoline performed much better than the knife in this respect. The testing of this metric was also one of the main reasons our original handle design was discarded, because it was very prone to instability when large vegetables were placed in the hole. Comfort was another important consideration, as many of the students expressed that it was uncomfortable or even painful to cut hard vegetables like carrots and potatoes, which is something we wanted to address with our design. So our handle design was mainly based upon trying to improve this metric. Initially, we tried to find a quantitative way of expressing comfort, but after reading lots of papers where other people tested the comfort of other designs, we realized that a qualitative survey of users would be likely sufficient for our purposes. And in this respect, our designs have performed very well. One girl expressed at Kohai that while it used to be painful cutting vegetables like carrots sitting down with a knife, it was now much easier and even comfortable for her to cut them using our Mandoline designs. Our survey participants in the school community also expressed that our new handle design was much more comfortable than the old design. And cutting performance is also something we needed to look at. All this design isn't really usable if we can't adequately perform cuts that are much better than the students could originally do. So we tested this using the standard deviation of the thickness of cuts with both our Mandoline and the knife. Using that and the qualitative observations you can make from the photos that we took, we can see that the Mandoline cuts are much more consistent than the knife cuts. Another important element for the implementation of this design is cost. Now we realize cost is a little bit difficult to consider in this case because we haven't actually built a physical prototype. So the cost that we're using is based on the estimation provided by SolidWorks, which is the program that we use to model and design our final prototype. We realize that this is a rough estimate based on material and manufacturing costs. It doesn't account for things such as equipment that we need to buy, but the value of less than $50 is much less than the established constraint of $100 per person. Lastly, while our ease of learning and intuitive metric failed based on our present questionnaire metric, through our discussion and verification with the teachers and students, we learned that almost all of the students felt that they would be able to use the device to more exposure, and all of them showed improvements in the 5 minutes that they had to use it.
I will now be discussing the next steps we'll be taking moving forward with the design. First of all, we will highly recommend using the design of any form along with these cut-proof gloves. Not only do they improve on safety, validation at the Kohai Education Centre proves that it minimally affects the comfort of the cutting process, effectively making it a net benefit process. Furthermore, we plan on replacing the silicone adhesive pads with Skin, which is an approved material that we have researched into that has a lock-unlock mechanism. Furthermore, we plan on adding more implicit cues to the design, which improves the intuitiveness of the design altogether. Next, we will research materials, although the two materials we're primarily considering are stainless steel and ABS plastic. Finally, we will look into the manufacturability before we finally release the product. We are now ready to answer any questions you may have.
So you can move around. You can move it around.
So the big concern right now is you mentioned that they want to be able to cut things like carrots and potatoes. How do they put a carrot in there? You said they'd have to cut it first to prepare it to go in there. How are you teaching them to cut the carrot in the first place? Because you can't do it here.
So we went to validate with them. That's a topic we brought up. So we asked them, with our design, it covers most vegetables. When it comes to the long ones, cutting in half would be required in order to use this. And we asked them, would that be something you would still consider doing? And they did validate that is something that they can still do. They agreed that it would be okay for students to learn to cut in half and then use our device in conjunction with
The main difficulty is repetitive cuts that require even spacing. Cutting something in half or even in quarters is not necessarily the most difficult part of the process. It's repetitive cuts. You have to cut a potato into slices or a carrot into slices. That's really the challenge. And having to use a knife once, especially with our cut-proof gloves, manages the safety risk and greatly reduces the difficulty.
Can you list to me all the vegetables that you can cut with your design?
So the vegetables that we have tested currently are, I guess including fruits, are apples, onions, cucumbers, carrots, potatoes, and tomatoes. but we are quite confident that other vegetables with similar textures and similar sizes would also be adequately cut by this.
Mandolines do already exist on the market, and they are capable of cutting the full range of produce that.
It's not the mandolin I'm worried about, it's the holder, because you're limiting the amount of different things you can now use because of the holder. Like how, when I cut a carrot in half, do I make sure the carrot stays vertical inside there?
The grip that holds the carrot in place, as shown by the model but not by our prototype because it was a little bit difficult to implement, is similar to the lid that we have now. The entire base is spiked, which goes into the carrot and holds it in place, which is one of the main factors that we consider in the Mandoline.
So that's what holds it in place.
How does it make sure a vertical thing inside of it like this, held to the top, when you're pushing against a sharp surface, doesn't bend?
If I may take this one, the spring lock in this iterative design also enables to push it at any orientation and allows it to remain stable as the spring is pushing it down along with the cushion.
No, I think he's asking for the fall over, right?
Yeah.
So the reason why it's a sponge in there and not an actual spring is because all the springs that we found were like too strong. The idea is you have to find a balance of force to try and make sure that it doesn't fall over, but ultimately it'll probably end up pressing against the side of the walls. So it'll be at an angle, which is a limitation.
This is a current limitation of the design, but there are things we can do to counteract it. With the Mandoline on the market right now, there's a hole slotted in the top where you can stick the carrot in and it's supported by the sides of the holder, as you can see there. And you can place the vegetable in there where it will be held. And we hope that we could implement something similar to our design.
You just say it doesn't matter. Who cares?
Well,
if it falls on its side, you'll still eventually get a whole bunch of slices that are the same. They'll just be a little bit bigger in cross-section.
I think the idea is to try and make available to the students at Kohai the widest variety of cuts available to people who are able-bodied, quote-unquote, because the idea is to make sure that, to eliminate the disability, so to speak, and to eliminate that barrier. And you want to make sure that they have as a wide variety of cuts available to them as possible, which is why I think it is important that they're able to make the same full range of cuts that we would be able to make.
Actually, I don't want to just apply those questions.
Talk to me about your reframing.
Yes.
All right.
Talk to me about your reframing. Because you took some instances off the shelf and whatnot. So show me why you ended up here and not something radically different.
Yeah, okay. So the main topic we brought up was the reframing of that overarching idea, where the original RFP framed it such that teaching knife skills was still a priority of the responding design. This honestly wasn't really mentioned as like an overall main. It wasn't blatantly stated in the RFP, but there were many small sections within the RFP that made this evident. For example, in one of the reference designs that they presented in the RFP, it said this doesn't work because it doesn't allow students to be independent with the knife. And so when we went to Kohai, these are the original field notes that Kamran took.
So, so these field notes basically I've highlighted the relevant portions for this question. So trying to approximate real life, so it'd be okay. So basically the idea was that Kohai is interested in teaching them practicals, like how to actually make stew, and whether or not they actually use a knife the way we would is almost superfluous. And so, basically, the stakeholder said if it was an automated process, we were asking about whether or not we could use a food processor. If it was an automated process, then it could produce if it could produce the exact same result as a knife, then it'd be okay. The idea is to make sure that they can do everything, or the vast majority of things that we could do, or people without their disability could do, but not to necessarily force them to comply with an image that we have of them using a knife.
If I may briefly expand upon, we found. To summarize, we found that our values reflected Kohai's values in that we were more concerned about the result, and we did not want to limit the students to traditional skills of holding the knife. And we thought that it was more convenient to provide them with a solution that streamlined the process and effectively made them available to the range of cuts that people without disabilities.
What are your maximum and minimum cutting thicknesses?
Of this design or
your design?
Okay, well...
So of this, off the
not
market...
the prototype, your design.
Our design. Yeah, Jen, you want to take that?
Sure, so the current design as it stands allows for, I guess, a wide variety of cuts. Of course, it's not suited for making very large cuts because we felt that the students were adequately able to perform these cuts, such as cutting a carrot in half per se. So our current design allows for cuts anywhere between 1 millimeter to about 10 millimeters thick, which we felt was an adequate size, and that's just on the main slicing blade. On the Julienne blades, we allow for dicing up to about 30 millimeters, which
How
is...
do you dice on this?
The way you would dice on this is, no mother attachment. Basically, if you're going to start at the, on our design, these Julienne blades are going to be double-sided. On this design, they're not double-sided. So the way you would dice on this is, you would start with your vegetable at the bottom, and you pull up.
Okay,
and on that,
slice up, turn, slide down. Okay.
Exactly, yeah.
How do you clean it with that thing that has a stopper now at the bottom so it doesn't fall out?
Well, you can pull it off the top.
Yeah.
That was the whole idea. If it can come off both ends, that's redundant. And
So when they're sliding up, what prevents it from, when they're pushing something to dice it, from sliding all the way up?
from pulling it off, well,
Yeah.
I mean,
You just
that
said
was
it could
never...
leave the top portion.
That was never.
So you're starting here, and you can't fall off the bottom. But when you're dicing, you're going to be going vertically with a lot of force, so it could fly right off.
Well, to be honest with you, when we were at Kohai, pulling it up off the mandolin was never an issue. It was always pushing down.
Because they were never dicing, because they were always purposefully cutting this way. But now you're dicing this way. So you are going to have a resistance that's going to be suddenly let go.
But with the Julienne blades that we currently have, they're much smaller and much sharper, which means on the way up, we're making less actual cuts than on the way down. So we felt that the downward force was more important in this case because, of course, we can only contain one of them if we wanted to make the whole mechanism removable.
And okay, and obviously, yes, it could come off the top, but it is ultimately a feeling that we're going to have to accept because it has to be removable to be washed.
Why can't you make the stopper removable?
Sorry?
Why can't you make the stopper on the bottom and top just a removable one? Or something that opens and closes so that you can just unlock it and take the piece out to wash it? Why make it permanent?
That is something we should probably look into. On the spot, the thing I see with that is just another moving part that the students at Kohai would need to use, which would add just another step of unintuitiveness to the device. That's something we can look into at a further point, but that's not something we've looked into at this point.
Question. I know you may not have done everything. Thinking ahead, looking ahead, let's say you want to have this manufactured. What are some specific considerations you'd be looking into for next steps for manufacturing?
So as Jay mentioned earlier, some of the main aspects that we looked into or want to look into are the specific materials that we want to make the mandolin out of. We're pretty set on making the surface out of stainless steel, but one of the things we haven't quite decided on is the type of plastic that we'll make the rest of the mandolin out of. So we've looked into ABS plastic, which is a strong, durable type of plastic, but there are other options out there. So that's something we want to look into for manufacturability. Anyone else want to add anything to that?
I would also like to briefly mention that in terms of releasing a final product, we also have to consider the cost of the molds created as part of manufacturing. We did mention that the cost is approximately $50, but that's from the user end. To create the molds themselves, it will be an additional investment from our end.
But this is an upfront, one-time cost that would eventually, if it were to be taken to production, would average out and even out.
Explain the use of this plunger. Why is it in your design?
So sure. So this is, I guess, an improvement based on the original design where in this one, if you place a large vegetable in the holder, the actual vegetable handle, like holder itself, would pop out of the...
I understand the purpose of the spring, but why do I have to see that protruding tip?
Because, so in this design, the handle moves down as you cut the vegetable. Because the protruding tip comes out, the actual handle stays at the same height, so it doesn't move as you cut the vegetable.
Why even have it? Why not just have the spring itself inside? Why have this piece that goes up and down there is what I'm wondering.
This allows easier force application here.
So now you're going to be pushing on the top of it.
Which may sometimes be required to insert the vegetable in because the spikes have to go into the vegetable. If it were simply here, when you push down on this, it would simply move the spring and the spikes would actually not penetrate into the vegetable.
If I may add something, it's also a visual indication as to how much of the vegetable is left in there. If you didn't have this pointing up, you would have no idea how much vegetable is left, and for all we know, someone who is developmentally disabled might just keep going even though it might be finished. So this also acts as a visual cue in order to show whoever is operating it how much vegetable is left to cut and when the cutting process is over.
Why not make the sides of it transparent?
The sides of it, I think, are transparent.
So then why do I need the thing to indicate what height it's at?
Because 2 indicators is better than 1.
Isn't it redundant? Adding cost for no
yeah,
reason.
I think that redundant communication ultimately just makes it easier for the person using the device to see what they need to see quicker.
But it costs me more. Can you justify the extra cost for something that's redundant?
Well, no, because you still need it to insert spikes into the That's okay.
If I may add, for the steps that
You're gonna have the stick anyways. It's just a matter of whether or not it moves out.
If I may add, for the steps that Yanchin mentioned earlier, it also provides more of an implicit visual cue such that they are aware of that functionality. Because one of the issues that we found was that they sometimes forgot steps in the traditional knife cutting process, and we're trying to streamline that as much as possible. As a parent.
Sorry, the other argument I would bring up as to why include a bar instead of just a spring is that if you just put a string on the inside, it's less rigid than something that's actually solid and fixed. So if you just had a spring in the top that pushed up and down, it's moving back and forth. And in a case where, let's say you want to put a carrot in, that's when it's going to start swinging and moving off to an angle. With this bar, it helps to prevent that.
You did, I remember you doing quite a lot of research. What was the give me an example of some research you found that changed the design the most? Had a significant impact on your design. I'm thinking research as opposed
Which one are you thinking?
Not Kohai research, not
actual research. I was thinking like the surgical one, because that's kind of. No, we still use it. That's
not to be perfect. Just one.
The power grip stuff that you found about.
Yeah, I guess. Okay. So basically, we were thinking of two main resources. This initial one was a study done on surgeons and surgical grips, and one of the main things we got out of this was. I can take it out and show you if you really want to.
Well, sure. If it helps, take it out.
Well, basically, one of the main things in here is that a joystick design. So, like when they were operating on surgery and it was robotic, joystick design was extremely stable for them. It was a very stable process, and that's what kind of gave us the idea of this sort of joystick handle.
You get those shoes.
That we found was extremely useful. This one, so the power grip. This one gave us the idea of how we should actually establish what handles we look like and what type of grip we should use for the handle. One thing we did look into was not food safety, but washing methods. So one of the things we looked at later...
The FDA standard for how to wash.
So we looked at FDA standards how to wash. No, it's right here. Yeah, so FDA approved washing methods, and this is how, it's a verified way of how to actually wash our mandolin. We also took this and we established a washing testing protocol that we want to implement at a later time. This isn't something we established at this point. This also takes use of ATP sensors, which basically measure the amount of food waste left on the surface after washing.
And bacteria.
Yeah, bacteria as well. But they're fairly expensive. That's why we haven't implemented it at this point. This is something we want to do looking forward.
How do you decide on the angle?
Sorry.
So the angle's adjustable because we didn't know. I mean, I don't say we didn't know which angle is optimal, but the idea was that they can adjust it to like which angle suits them best. And so I mentioned it. There's a ratchet mechanism. This is this here. Here you kind of just have to set down to like the one setting. But the idea is that there'd be like ratchets here, so you can choose the setting that you want. That's ideal for your forceps.
So how high and low can you go to stable positions?
Yeah, so the highest position you can go right now is about 45 degrees certain angle down. The lowest that you can go is theoretically, however, like close we space the ratchets, which we haven't entirely considered yet. It's something to look into for manufacturability. But
how did you choose being able to go to 45? Was there a reason you wanted to be able to go up to 45?
I think it was more for practical purposes in that most people wouldn't want to, it would be, reduce the ergonomics if you had to like reach your shoulder up to push down. Because in that case, it would be more of a downward position. And eventually it would also be very hard to hold in place because it would be sliding down the platform.
FPD diagram on the angle. You want to show that?
Right. So one other thing we looked at was just the angle of we did FPD analysis of the angle of the mandolin as well. This was mainly for like standing versus sitting, but it can also be applied to the angle of the mandolin. So if the angle isn't attributed or at the level that someone's hand is basically going parallel to the plane, there's going to be a component of the force that's not in the direction of pushing. And so that's one of the reasons why we said standing, but that's also one of the reasons we made it adjustable, so that whatever height you're at, getting it to waist level is going to be easy, so that you can push directly down the plane and apply all of that force parallel to the mandolin surface.
In addition, one of the next steps that we do intend on taking is investigating what angles of the user itself, and then adapting the angles available on the Mandoline to fit more towards that, because that was an area that we needed resources to fit.
Measuring the joint angles generally was something that we did not have the time or resources to do at this time.
Show me one of your earlier design other than that one.
Another design other than this one.
Oh, the posters.
We do have the posters.
Okay, so these are the basically how you beta, and they still have our own prototypes on this. Yeah.
So, let's see. These are the other designs we came up with. You were here for beta, but Melanie, you were. One of the other ideas we were considering was this one, and we call that the blade press. Essentially what it is was, like, we would take the cutting board itself and basically attach hinging blades onto it, so that when someone is cutting a vegetable, all you need to do is put the vegetable down, push down the lid, and then all of the cuts would be made instantly. One of the main issues we saw with this one is that in order for these blades to vary in thickness, someone would need to be able to remove the blades and put them back in, which is inherently dangerous. That is the main reason we eliminated this design in our earlier process, but that is one of the designs we were considering.
Oh, okay, so this is the prototype we had for beta of blade press. Thank goodness for Yanchi. So yeah, this is it.
Can you show me 5 more very thick slices on the apple?
Yeah, sure.
You don't even need to stop her. I just want to see you do 5 more thick slices.
Well, we need
to put the thing on. I mean, I can do it by hand. But
Yeah, you can do it by hand.
Oh, you want to do it by hand?
I just want to, not that guy though. I want the one that you already have over there.
This one?
Yeah.
Gotcha. Okay, so this is the thickest setting that this manual has, just to be...
Yeah, I just want you to do 5 more thick slices. What do you think for kids to have something like this slice? Is that usable?
No, that is not usable. That is something that needs to be taught at Kohai. Our intention is to make the slices available. It's the teachers at Kohai that should be the ones to teach them how to use the mandolin and what food is appropriate to use in the cooking process.
We are giving them the tools. We're not necessarily going beyond in terms of what results to use, although we trust that the teachers at the Kohai Education Centre more than to see them in that way.
We'd also like to point out that in the RFP, originally we're not like coing apples or coing like fruit is not part of the scope. The vegetables that we need to be able to cut are tomatoes, potatoes, carrots, onions, cucumbers. So all those can be cut with the mandolin. There is additional functionality, obviously, but coing apples, that sort of activity that you can also do with a knife, is not part of sort of the scope. It's slicing, dicing, yeah.
Thank you so much. Have a good time.